Welcome to my dear student and researchers. So today I am going to elaborate one very interesting topic. Okay, so before to go in details, because who are working with this is related to structural mechanics, solid mechanics. So who are already working with that, they know very well. I'll first show one picture. You see, so here what has happened, you see, this is a table. So when newly, after purchasing, when it is purchased newly, some books kept, that time this kind of bending was not there simply, and over the year, say after 1 year, if you keep it like that, after 1 year or 6 months or 2 years, it started to bend like this, and over a certain period, this crack happened and it failed. So this phenomena is called creep. So today we are going to discuss by simulation method what are the technique to find the creep remaining useful creep life of a structure at constant load. Okay, so basically creep is defined in the word of structural mechanics that it's a time dependent permanent plastic deformation under constant load. Okay, so hope you understood what is creep, and it is a time dependent, it's a time dependent event. It may take long time to fail. It's a gradually that it will fail. It will not happen suddenly. Okay, it will take more time. So when there is a constant loading, you should know what should be the life of that. So for that, this creep analysis is very important. Okay, so now if we characterize this creep, so basically if I plot a curve, so this is my x-axis, so this is my x-axis, so which is time axis. Okay, and this is the y-axis, which is my strain. Now over the time, for a constant load, okay, if you see, so the curve will be, so there will be some initial strain, so it is like this, then it is like this, and then it is like this. So you see, this curve is segmented into 3 parts. So this is called, this part is the primary strain, and this area is more or less it will be constant. It is the secondary part or the steady state part, and after that this part is called tertiary part. Okay, and as I told, this is a temperature dependent event, so this is for one temperature. So now if you elevate the temperature, the curve, the nature of the curve will change. So it may go like this and this and like this. So this is the temperature, is some higher temperature. If you take further high temperature, so it may come like this. Okay, so this, say this is this temperature is T1, is higher than, say this is T2, which is higher than this temperature, say T3. So that's why it's a temperature dependent event. So now the question is, if anybody want to find that I have one particular structure and it having a constant load of that, then due to this creep, what is its remaining useful life? How long it will not fail? So there are several methods are available. So today I am going to tell one simple technique through which you can predict it. You can go for, so normally we will be working for this to predict it by machine learning method. We will be using a convolutional neural network to find out that creep remaining useful life of the material. Okay, so this we will be how to conclude that this will be the remaining useful life. So we will be mostly concentrated on the steady state part, because this part to equate this part, it will be very easy to formulate or to predict this, or to find out this part is easy, because it's a linear part. Okay, so here this curve having, so this rate, if I ask what is the steady state strain rate, so I am denoting it as epsilon dot steady state. So this steady state strain rate is nothing but the slope of this curve, so which is del epsilon by del t. Okay, so if we can able to find out that the time versus the strain curve, okay, then from there we will know that what is the elongation or what is the strain at yield point. So anyhow, in any structure, if the yield reach, then we can conclude that it is about to fail. So to reach that yield point, if I know the strain at the yield point, then we can predict how much time it will take. So basically we are going to find out this. Okay, so in creep behavior, this steady state strain can be equated by this Arrhenius style equation for temperature dependent reactions. As I told, it's a temperature dependent, this creep is a temperature dependent event under a constant load. The material will be okay. So we know the general this is the formula for, or this is the representation of general Arrhenius style equation. It is some constant into e to the power minus EA divided by R into T. Okay, so here A is some constant and this EA is called the activation energy. Okay, and this R is the gas constant and T is the absolute temperature. So in case of creep, this is written as some constant, say K, into sigma to the power n into e to the power minus qc by RT. So here it is similar. So this is a material constant, and this sigma is the applied stress, that is the constant loading, and this is the, you can tell, it is also depend on the material. It's a, you can tell it's a stress exponent, and this is QC is the activation energy for the creep, and R is the gas constant, okay, and T is the absolute temperature. Okay, so now our target is to find these all parameters. So in this equation, this K is unknown, our N is unknown, and the QC is unknown. So unknown parameters are K, N, and QC. So basically we will try to find out these three. Once these three we found, then we can fit the curve. Okay, we can fit the curve and we can find out this steady state strain rate. Okay, that means the deformation, the deformation per unit time. Then we know already what should be the strain at yield. To reach that, how much time it will take. That is the remaining useful life for the after that only the structure will fail due to constant loading. Okay. So what are the things are here? What are the things are here? This will, based on that it will vary, because if the material is the same material, then K and N will be the same, okay, and QC also it will be the same. So we can vary the applied stress and the temperature. Okay, so for a same material, we will get, then we can get the different, that we will get the different curve for that, and we can estimate it. Okay, so these things is normally difficult to find out by actual testing. So instead of that, what we will do, we will use the finite element modeling, as it is a time dependent analysis. So you have to go for the transient analysis, so it need very high memory. So say there is a structure. So now I will go directly to the simulation part, because entire thing we are going to do by simulation only. I am using COMSOL Multiphysics. So as I told you, it will be a transient analysis, so it will take a lot of time. So I will make one small model, and I am showing here just only the techniques. So you select the 2D, and here you use solid mechanics. Go to the study. It's a transient analysis. then you use, this is the unit, this one, and here this model will be linear elastic material. You use linear elastic material model because we are considering all this parameter within the yield. So here simply I will take one small rectangle, it may be 10 by 100, okay, then build selected. So it is like that. We will go to geometry, it will convert into solid, okay, then we will go to, sorry, then we will go to material. So we will add material from library, say it is iron. Okay, so this is the, I am using this one, it is defined. So the material, so what happened? So this is the material, one minute. So add to component, so here I know it, okay. So my, here my material is iron, it is already selected. So these things, what we will do with a different load, with a constant load, we will try to plot the time versus, because it's a time dependent analysis. So my x-axis, so what we will do, so what we are going to do basically, so my x-axis will be time and this y-axis it will be strain, and this curve, this rate with that particular load, we try to find out this curve. And if you find out this curve and if you get this angle, then that is my strain rate, the change of, that is the change of strain with respect to time. So for that, how to vary the temperature, you go here and here you see the common, this is the temperature. You can change the temperature here with different temperature, elevated temperature. You can give sometime room temperature, sometime, because as I told in the equation here 3 unknowns are there. So to find out the 3 unknown, you need 3 equation, 3 this kind of equation. From there only you can find out. Okay, from there only you can find out with different temperature. So you can vary, you can keep this sigma same, and you can find out this rate, because as I told, this will change. If you change the temperature, this curve will, another temperature, another elevated temperature, it will be maybe like this, another temperature, it will be like this. So you will get 3 equations. From these 3 equations you can find out, or if you can generate lot of data set by fitting a neural network you can also do that. There are several ways. So you can change your temperature here. Say now I will be doing it for say 400 Kelvin. Okay, then simply I am showing a simple analysis. So it's a fixed constant, say let this part is fixed. Okay, then you apply one load, so that should be your boundary load. So your boundary load, I will give the load to in this direction, so that will be negative y direction. Say that is 5 Newton per meter square. Okay, then you go to mesh. You create, it is a simple thing, and time dependent. Here this time you can change. If you change it, say I am changing it to 10 seconds. So you try to make it as more, this will take more time. So I am not showing that one. As much as possible, you based on your computational capability, whatever possible thing, you do that. Okay, now I am computing. See, it's a very small structure, it is very quickly. Now you see, you have got the stress plot. So now you can find out the strain curve. From this analysis you can find out the time versus, you can find out the time versus strain curve. So that means in three different value of t, you will get three different this strain rate. Okay, so if you got that, then by putting this, by do the solution, you will get this equation. Okay, now from there, from these things, if you're for a particular, if this Kn and Qc is known, okay, then you can estimate it. You can estimate its remaining useful life. So this is a simple technique I have told, because my computer having a I have shown you just the technique. Okay. And one more thing, you consider this applied stress. The applied stress should be within 10 to 20%. While you will be doing the simulation and getting the result, this you can take 10 to 20% of the yield stress, not at the higher value of, because creep it will not happen due to more load. Okay, because your design margin will be there. So you use 10 to 20% of the yield stress, and you with different temperature you find out that, so that any temperature you can get the rate, and based on that you can find out the, even though it will be very this value, it will be, to estimate this value by simulation also, it will be very, this value will become very negligible value. So you should be very careful to do the simulation and its meshing, its relative error during the simulation. All these things you have to take care. So hope you understood what I tried to explain. For any further query, you can write to me. My details will be there in the video description. Thank you so much. Thanks for your patience.